All right, so let me address why iteration tends to be something that shows up in computational fluid dynamics, but is not always present as something you need to look for in finite element methods for just like, let's say, conduction problems. So why does this come up in computational fluid dynamics? It's basically this convective term. So in our generic form of the finite volume method type problems, you've got a convective term here that you're taking the divergence of, and we showed that using the divergence theorem, you can take the volumetric integral and turn it into an area integral over the faces, and then basically what's required is to estimate the value of rho times u times phi dot n, or it's really u dot n, on the faces. So we need that average value on the face times the area of each face. Let's take a look at like what this thing is. So so in this problem, phi is generally an unknown that you're solving for. But you know what? It's a convective problem, so actually we don't generally know the u's ahead of time either. So that's actually part of the solution process. So like, let's just imagine a particular scenario for the moment to make this simpler. So let's suppose that phi represents, let's say, u sub x, so the velocity component in the x direction. So let's say this is like the x momentum equation, for example. So this is the x momentum equation, in which case phi is u sub x. So let's try to like bust this thing out and see what it is. So I don't know. Let's imagine that I've got some central unit cell, and then there's a bunch of adjacent unit cells to it. I don't know. Let's call them the central one. I'll call this the east, north, west, and south cell, for example. And then like in principle we would need to like write this out for each one of the faces. There's 4 faces here. So let's see. So we need to write let's see, rho ux, and then let's say u dot n on whatever face it is, like the sum of this over all the different faces. Okay, why don't I'm just going to highlight one of them here. So let's take the east, the connection between the centroid and the east face, for example. So let's bust that out. So then on the east face, that looks like rho times u, let's call this ux on the in the eastern cell, plus ux in the centroid divided by 2, let's say, for a central scheme. And then I need to do that, then I need to calculate u dot n also on this face. Well, u dot n really is just u, right? Because in this case, n hat is actually sitting in between. So again, that value is the same thing. It's ux east plus ux center, or centroid, divided by 2. And so, that term, just the terms associated with that connection right there, involve unknown values of ux. So the ux's are all the unknowns. But in this case, if I expand that out one more time, so this is just the east face, the term associated with the east face, that would be rho over 4 ux east squared plus ux central squared plus, I guess, 2 times whatever's in between, right? The cross term. So the important bit here is that After I convert all of this stuff into algebra, so remember, these are my discrete values that I'm trying to solve for. I'm trying to solve for the discrete values of ux at these different centroids. So in this case, because I was looking at this connection, I generate, connections between, values at the east and central regions. But the important bit is that instead of ending up with, let's say, ux with some pre-coefficient, I have ux squared. That means that this is a nonlinear algebraic equation. So whatever, I can do this for the other faces as well, and I'll get more additional nonlinear terms, but the key thing is that I don't get a linear algebraic equation at that point. I get a nonlinear algebraic equation. So we have really good solvers for linear algebraic equations, like ax equal b type problems, but we don't have really great linear algebraic solvers or we don't have algebraic solvers that are general for nonlinear problems. So in these kind of schemes, you end up using, iterative algebraic solvers, typically like a Newton-Raphson method type solver. And in that case, you need to, let's say, start with an initial guess for what you think the values of all these things are, and then keep iterating until you solve the algebraic equation using, let's say, the Newton-Raphson method. So that's basically the issue. And so, because you have these nonlinear problems, you have to use an iterative solver, and then to figure out, well, I'll talk later about how you actually figure out when you're done solving, but the idea is that you basically never actually reach the exact solution to these things. You cut them off whenever you see that the algebraic equation is close to being satisfied.